Okay? Now let's look at the recipient, the other individual. We'll make this the full sib. Okay, the full sib, by descent from a common ancestor, identical by descent from a common ancestor, has half the gene, or has the gene half the time. Now the rest of it is going to be made up of our good old P's and Q's. P, Q, P, Q. So natural selection striking this part of your loci or genome and that part cannot change gene frequencies because it hits the genes in the frequency with which they already exist. So a third of the time it gets a benefit, let's say, or let's say here, a third of the time it suffers a cost, because you're suffering a cost to transfer a benefit if it's an altruistic act. You know, a third of the time it gets a benefit, but 2/3 of the time its alternative gets the benefit, and that's the ratio at which they're found. So by simple logic, the frequency with which the allele has, the frequency the allele has achieved does not change the direction of selection. It still remains the case that it is only the correlated portion of the genome, as we like to call it, that determines the direction of selection. The fact that you definitely have a gene, and the fact that putatively your brother or sister has it half the time. The only difference, the only effect of this section of the genome is that it will slow down selection. Let us say, for example, that you're dealing with behavior toward a cousin, then this is only a quarter of this is only occurring an eighth of the time, sorry. And so it's smaller, which means the uncorrelated section is bigger, which means that the forward selection of this gene is slower because you're wasting more of the time taking the red and blue balls out of this box at random, increasing them or decreasing them and flinging them back in. Okay, fine. Now, how far have we gotten? Okay. Now, is there this possibility? Is it possible now for a gene to recognize itself and confer a benefit directly on itself? Or does it just have to rely on indirect evidence that the other individual has the gene because of descent? So this was popularized by Dawkins with the name green beard, because it was a gene that gave you a green beard and then gave you the impulse to like individuals with green beards and to transfer benefits to them. So it's a green beard gene that recognizes itself phenotypically in someone else and transfers the benefit. Now, you may have noticed that green beards are infrequent. And indeed, this kind of gene is very, very infrequent. I will mention one kind that's kind of a special category, but we've had cases that people have pushed forward, and maybe one or two have survived critical scrutiny, but that's about it. It's a very, very small category. And the reason we believe that's true is that the rest of the genome ain't going to be happy with it. If I've got a green beard gene that gives you a benefit just because you got a green beard, all the rest of the genes in me that are not linked to this green beard gene are not going to be happy with my wasted investment in you, because they don't share any resemblance to you. So a critical feature of kinship is indeed the fact that it tends to work across our genome. Not completely. And that's a whole separate world, which I'll touch on in 1 second. But in general, across all our autosomes, if I'm half related to you at this locus, I'm half related to you at every other locus. So they're all in agreement that we're going to act nice whenever B is greater than 2C. So in Other genes in you are going to be busily selected to shut down green beards if and when they appear. There are some exceptions to this, and let me just mention one. And, you know, does anybody have a watch they would consider lending me? Thank you, brother, because, you know, Doran can get pretty ugly towards the end of this. So what is the end? When am I supposed to shut up?
It's 5:45.
5 what?
5:45.
5:45?
So
Jesus
people have
Christ,
a chance
Doran,
to
I
ask
better
questions.
pick up the speed of this.
If you have, you're, 5:50 if you want no questions.
Okay, thanks for that choice. So, one example are cell adhesion molecules that are homophilic and operate in human pregnancy. So basically, you've got a cell, and then you've got a molecule here, and this has some shape in here. And it connects with, let's make this thing out like this, and let's just say that it chemically bonds with the same damn molecule in the mother, which also has its structure down here for what it's supposed to do. So this is mother, this is offspring. And it will, if there's a match, tend to suck resources from mom. And the interesting case turns out to be when she's heterozygous, so that some of the offspring have the gene that's going to hook up and some don't. But the point is that within the individual, I'm completely happy with this homophilic gene getting more resources from mom that are going to other fetuses, as long as it's not too great. You know, as long as the costing isn't twice the benefit if we're full siblings. So there can be circumstances that then spread through to fixation, and then afterwards you don't even think of it as a green beard effect that went to fixation. You just think of it as mother-offspring coadaptation at the placental boundary. Okay. Now, this I cannot state for you well, and my apologies for it. People who are mathematically talented claim that kinship can be restated in terms of group selection, and the statements, if done properly, are isomorphic. Group selection, when done properly, talks about within group variance and between group variance in genetic traits, and compares the two. And then it has to have rules regarding the formation of new groups and blah, blah, blah. I call a friend of mine who's an expert in kinship theory, and I say, look, when you apply this to just two individuals, you and me, who's the group here, and how do these group people do it? Because I don't bother thinking about kinship in terms of something more difficult, group selection, than simple kinship theory, simple probability. And he said, and I don't know whether this is true, that he thought, because he's like me, he thinks in this system and not the group selection one, that they set up systems where the group of him and me actually consists of different alternative individuals that may both have the allele, may have one allele and the non-allele, and have neither allele, and then you have the combinations with the other three individuals, and you somehow work out all that, and you come up with B greater than 2C for full siblings, let's say. Then all I want to say is, and you people must know this much more deeply than I do, just because two languages are isomorphic or can be made isomorphic does not mean that they're equally useful in thinking about things. And the simple approach to kinship theory that I've tried to give you can lead you quickly into seeing novel things which, if you had to formulate them originally in terms of group selection, you still wouldn't see them. And I just give you one example, because when people argue this group selection stuff with me, I say, fine, how many centuries would it have taken you to think up genomic imprinting? Yet the logic was thought up very, very quickly based on simple kinship theory. What is genomic imprinting? Well, let's look at your degree of relatedness to your half-sibling related through your mother. And we start with you always, and we want to know what the chance is, identical copy, in your half SIB. And so degree of relatedness equals a half times a half equals a quarter. Now that is with complete ignorance. Ignorance, i.e. the gene here does not know where it came from. Now let's give it knowledge, or complete knowledge, exact knowledge, any way you want to word it. Now we have a situation where we could have a maternally active gene that knows it came from mom, so to speak. It is related to mom by 1, and there's a half chance she passed it down. Sorry, this is so ugly. And so therefore, degree of relatedness for a maternally active gene equals a half. Or it could be a paternally active gene, in which case we know it didn't come from mom, and 0 times a half is 0. So, R for a paternally active gene equals 0. And you can think of the quarter as being the average of these two, or as genomic imprinting permitting you to segregate 1/4 into a half and a 0. Now, I said paternally active or maternally active, and that's precisely the mechanism of memory that has evolved. That is, we now believe that there is up to 5% of our genome consists of genes which are, the copy from one parent is active, the copy from the other parent is inactive. So you have paternally active genes where the identical genetic structure, the identical base pair structure, if coming from mom, would have been turned off, silenced. And that's why they called it genomic imprinting, because there's some imprint put on the genes during oogenesis and spermiogenesis that turns them on or turns them off, independent of their DNA structure. And likewise, you can have the reverse. So whether the gene knows anything about this or not is all irrelevant. The point is, a paternally active gene can act as if it is sure that if it is active, it did not come from mom. A paternally active gene, put a different way, had to come from father. It could not come from mother, and the same thing's reversed for maternally active. Well, as I say, I'm just using that as an example. That's, by the way, a fascinating and extremely important area. And when I told you earlier that it wasn't quite true when I was using this man as an example of degree of relatedness of a half, I said it's across all our autosomes. Well, the X and the Y, it's different. Mitochondrial DNA is different. But now we know our maternal and our paternal genes see the world differently. And that's half our genome against the other half. And it has very important effects early in life, but now we know it has effects all throughout life, in the life of mice, humans, and some other creatures. Okay. Well, good. That leaves us next to no time for reciprocal altruism. So let me just talk about reciprocal altruism briefly. So my first paper was on reciprocal altruism because Hamilton had come out with kinship theory. And yet it was obvious to me, just looking around the room, that there are people that are friends of yours to whom you are negligibly related, yet to whom you may have warmer feelings than you have towards some, or indeed many of your relatives. You may have heard the folk expression, you get to choose your friends, you're stuck with your relatives. And that's one reason why we can feel real close to a friend. So I said, well, let's try to model this. Let's try to model altruism and good feelings and blah, blah, blah between individuals to whom relatedness is not the key. And so the notion was very simple, reciprocal altruism. If you scratch my back, I'll scratch yours, but with a time delay. If we're scratching each other's back simultaneously, we can adjust things so that nobody's getting cheated too bad. But if you do something nice for me and you gotta wait 2 weeks for the return benefit, and then, do I remember, am I around, do I give you as much as you gave me, blah, blah, blah. So you have the problem of the cheater. And the cheater, in turn, comes in two forms. A gross cheater who doesn't reciprocate at all, that's easy to discriminate against. And the much harder one is someone that reciprocates, but not quite as much as you would if the shoe were on the other foot. Out of that, I thought, came, yes, feelings like friendship and so on, but also eventually a sense of justice. I don't think